Hi, you're 8. Today we're going to look at current and potential difference in a parallel circuit. So by the end of this lesson, you'll be able to see how to measure current and potential difference in a parallel circuit. You'll be able to state the differences between the series circuits we looked at last lesson and the parallel circuits we look at this lesson. You'll be able to predict using models what happens to potential difference in current in a parallel circuit. And for some of you, you'll be able to predict what would happen to a bulb if it blows in a parallel circuit compared with a series circuit. So today after the starter, we're going to be modelling parallel circuits to predict what will happen to current and potential difference. We're then going to look to see whether our predictions were correct, first of all by doing an experiment on potential differences in the parallel circuit, and then going on to look at an experiment with current in a parallel circuit. And then finally, we're going to consider the differences between series circuits we looked at last lesson and parallel circuits we look at this lesson. First of all, I'd like you to do a starter. So this links back to last lesson. As you add more bulbs in series, what's going to happen to the following? The brightness of the bulbs, the current flowing around the circuit, the potential difference across each bulb, and the total resistance of the circuit. And secondly, what happens to the other bulbs in a series circuit if one blows? Pause the video, have a go, and I'll go through the answers in a minute. So let's take this example to see whether you're right. I've got a 6-volt battery, therefore on its own the bulb will also have 6 volts across it. And let's just say the current flowing round was 0.8 amps. If I was to add another bulb in series, then of course they share the potential difference of the power supply, and they share it equally if they're identical bulbs, so they'll have 3 volts each across them. And because the resistance is increased because current can only flow one way, and so the resistance increases, it's got to flow through 2 bulbs, the current drops. And of course the brightness is less with 2 bulbs than it was with just 1. And secondly, if this bulb was to blow, then there's no electrical connection for current to flow, and so the other bulb would go out. So let's start by modelling parallel circuits to predict what will happen to current and potential difference as we add a bulb in parallel. So this was a series circuit we did last time, just to remind you. We had 2 3-volt batteries, so 6 volts in all of the power supply, and so as the charges went through, which were the students, they gained 6 joules of energy, 6 sweets. As they go through each bulb, they give identical energy to each bulb. They share their energy out, and so each bulb only receives 3 joules per coulomb of charge, so 3 sweets. And therefore, the potential there is 6, because the charges are carrying 6 joules. The potential there is 3, and therefore the potential difference across there is 3 volts. The potential there is 0 because they're not carrying any energy, electrical energy, and so the potential difference there is 3. So you can see that they share that energy and that potential difference. So what happens in parallel circuits? Well, what I've got this time is students going around a parallel circuit. I've got 2 paths that the charges of students can flow around. They're all carrying 6 joules of energy here. And what I want you to do is have a look at that model and decide what you think happens to the current flowing around and what you think happens to the potential difference across the bulbs. Pause the video, have a think about it. I'll go through it in a minute. So firstly, the current. Well, when the student gets to here, the student can't go both ways, or the charge can't go both ways. So some will go one way, and some will go the other. And because the bulbs are identical, then half will go one way and half will go the other. So suppose we had 4 amps flowing here. Here would have 2 amps flowing, and here would have 2 amps flowing. And of course, as the students go around here, they're going to join up again. So we'll get 4 amps flowing here, the same as we had flowing out. So what about voltage? Well, whichever way the students go, they are carrying that 6 joules of energy. And so they're only going to go through 1 bulb each, and therefore they'll give all the energy to whichever bulb they go through. and therefore the bulb is receiving 6 joules of energy per coulomb, so voltage across each bulb will be 6. Notice that their voltage is identical to the voltage of the power supply, which is also 6 volts in total. So voltages in parallel should be identical to the supply voltage. So let's look at that in experiment and see whether it's right. Notice when I add a second bulb in parallel, it doesn't actually affect the brightness of the first bulb. And the voltage across the first bulb reads 5.92, which is roughly 6 volts. Measuring the voltage across the second bulb also reads 5.92 volts, roughly 6 volts, so they're identical voltages. And just to check, measuring the voltage across the power supply gives us 5.96 volts. That's roughly 6 volts, which is about the same as across the other 2 bulbs. So bulbs in parallel are identical. I'm now going to add 2 identical bulbs in series in the second path. So you can see those 2 bulbs are in series, but they're in parallel with the first bulb. And notice the first bulb is still really bright, but the other 2 bulbs in series are dimmer. Measuring the voltage across the first bulb, it still reads 5.95 volts, which is roughly 6 volts. If we now measure the voltage across both of the bottom bulbs, it still reads 5.96 volts, roughly 6 volts. But because those 2 bulbs at the bottom are in series, they share that 6 volts, so roughly 3 volts each. Just as a quick extension to help you with your worksheet, I'm now going to change the 2 identical bulbs at the bottom for bulbs of different resistances. The red and green bulb just refers to the coloured dot on the bulb so we can identify them, but you'll notice that the green bulb is much brighter than the red bulb. It has a higher resistance and takes a bigger share of the energy. So if we now measure the voltage across each bulb, the bulb on its own in parallel has 6 volts across it, the same as the supply voltage. The voltage across the bottom section also has a voltage of 6 volts across all of it, because whichever way the charges flow, they have to lose 6 joules of energy. But because on the bottom section the 2 bulbs are in series, they share that 6 volts. So the red bulb with the lower resistance takes about 1.4 volts, and the green bulb, which has got a higher resistance, takes about 4.6 volts. Notice those 2 voltages, 4.6 and 1.4, add up to 6 volts. Now let's have a look to see whether my predictions for current in a parallel circuit were also correct. So at the moment I've just got a series circuit with 6 volt power supply, and I've got 1 bulb, and the current flowing around the circuit is 0.3 amps. What we're now going to do is add another bulb in parallel and see what happens to the current flowing out of the power supply. So you see the current suddenly jumps to 0.6 amps flowing out. It has actually doubled. Notice the brightness of the first bulb was not affected by adding the second bulb in parallel. So now let's measure the current flowing through each of the bulbs to explain why the total current doubles. So the current flowing through the first bulb is 0.3 amps. And the current flowing through the second bulb is also about 0.3 amps. So current in the circuit splits. 0.3 amps flows one way, 0.3 amps flows the other. So what should flow back is 0.6 amps. Let's check if that's right. And yes, it is 0.6 amps. So current splits at a junction in a parallel circuit. Half goes one way and half goes the other if they're identical bulbs, and it joins back up at the end. Finally, let's round this up by looking at the differences between series and parallel circuits. So let's start off with current. In a series circuit, current is the same all the way around. In a parallel circuit, the current splits at a junction. Half will go one way and half will go the other if they're identical bulbs, but whatever flows through each path will add up again. In series, the potential difference is shared between the two bulbs. In parallel, the potential difference isn't shared, it is identical to the voltage or the potential difference of the power supply. So if you add more bulbs in series, the brightness of the bulbs goes down. If you add more bulbs in parallel, they have no effect on the other bulbs, so they all work properly at the same brightness. Finally, if one bulb blows, or in a series circuit, all of the bulbs go out, there's only one way that current can flow. Whereas in parallel, if one bulb blows, then current can still flow through the other paths, so the other bulbs aren't affected. Now, years ago, Christmas tree lights used to be wired in series. So when you got them out for next year, there's always the case that one bulb will have gone. And so when you turn the lights on, nothing happens. And the only way to check them is to get a good bulb and unplug each bulb at a time and put a new bulb in to see whether they light. Whereas nowadays, they're wired in parallel, which means if one bulb goes out, the rest stay on. So when you plug it in, you can see just one bulb's gone out and you can replace it because all the rest are still alight. What I'd like you to do now is to go on to the worksheets and have a go at those that are attached to this lesson. And I look forward to seeing you next week when we're going to do resistance and look at how we can calculate resistance using Ohm's law.